Hi there, and welcome to my channel. My name is Mikhail Zotev, and today we're gonna talk about a topic that seems complicated to many developers, but is essential to creating complex scrolling effects with Flutter. Slivers. If you have used a list view or a grid view, you have already worked with them, but not directly, without even realizing it, doing this behind the scene. Today, we'll explore why do they exist, how do they work under the hood, and how this knowledge will take your ability to create scrolling effects to the next level. Let's start. So, first of all, why do slivers even exist? What problem are they solving? And to answer this question, we need to think about what are they part of. Slivers are the foundation for scrolling system. And when we talk about scrolling system, we talk about a very specific way to build layout. But who are actually responsible for layouting in Flutter? Correct, it's render objects. Regardless of which layout protocol is used, layout in Flutter's render objects always follow the same three core principles. Constraints flow down from parents to child. Sizes flow up from child to parent. Parents use that size information to position their children. Let's take a look at the simplest and most common case of layouting in Flutter. How it works with the box protocol. Box protocol is what powers the most everyday widgets, columns, row, paddings, and so on. It's called box because both constraints and sizes it deal with essentially rectangles, boxes defined by width and height. To describe these constraints, Flutter uses four properties: maximum height, maximum width, minimum height, and minimum width. The child receives these constraints and chooses a size that fits within them. In other words, it picks a size from the intersection of those two rectangles, maximum and minimum. The size is also rectangle, like this, or this. But here's the catch. The system works great as long as children are smaller than or equal to their parents' available space. But for scrolling it does not work, because scrolling is necessary when the amount of content we want to show is larger than we have space for it. In other words, scrolling is overflow by design, and that's something that box protocol was never meant to handle. This is exactly where a separate layout protocol is necessary, and in Flutter this special layout protocol, Sliver protocol. Since it's still a layout protocol, it follows exactly the same three rules we discussed earlier. Constraints go down, sizes come up, and parents position their children. But the key difference, instead of working with the simple rectangles, the Sliver protocol uses more complex structure to describe constraints and layout result, Sliver Constraints and Sliver Geometry. Now that we understand why all of this is necessary, let's move to the next question. How does it actually work? Before we dive into how scrolling implemented specifically in Flutter, let's take a step back and look at the problem broadly. What do we actually need in order to implement scrolling? At its core, scrolling is always a form of user interaction. Whether it's swipe on a touchscreen, a scroll a wheel on a mouse, or a drag gesture, scrolling always starts with a user input. And we need some kind of system that can capture this user's intent to start scrolling and respond to it appropriately. But capturing user input is just one part of the equation. We also need a dedicated object that capable for the next things, showing more content than we have a space, coordinating relation between layouting, constraints, and showing only those part of content that should be visible now. But the content itself is not ordinary either. With the scrolling, we often apply specific scrolling effects, like sticky header, parallax section, snapping behavior, or collapsing toolbar. So the content we scroll need to be able to behave differently under different conditions. Now that we have looked at global challenges implementing scrolling, let's see how Flutter addresses each of them. And there are special implementations responsible for each topic. For capturing user input, there is Scrollable. For acting like a container that can scroll more content than there is a space and handle all management, we have a Viewport. And for defining how each piece of content behaves during scroll, we have Sliver widgets. Let's take a look at them one by one. So, Scrollable is arguably the least interesting part of this tree. If we check the documentation, it's literally a widget that knows how to scroll. And that's pretty much all it does. It listens for user gesture and passes this information to the viewport. It fulfills its responsibility, capturing scroll input and then get out of the way. That makes it the least important piece in terms of customization. In fact, it's rare that you ever need to work with Scrollable directly. The one thing that might actually be interesting about Scrollable is that it defines the scroll behavior, things like scroll physics and how motion is interpreted. But this is big enough topic and we won't go into it in here. Customizing scroll behavior is its own separate rabbit hole and it's not something that we'll cover in this video. Now we move on to the next part, the viewport. Viewport is at least more interesting. First, because even though it's unlikely, you might theoretically find yourself needing to implement a custom one. But more importantly, because it's a true workhorse of the scrolling. It's responsible for deciding what to show, where to show, in what order to show, along with many other internal responsibilities. The internal structure of a viewport is fairly complex. And as I mentioned earlier, it's quite unlikely you need to implement one from scratch. But it's important to understand what properties and capabilities a viewport has. That's something that you might need to work with slivers. And the first thing we need to determine, which makes perfect sense for a container that scrolls its content, is the direction of the scroll. For simplicity of understanding, I'll show visualization for the most used case, default vertical scrolling. Viewport has axis direction to indicate the axis along which scrolling occurs. It can be vertical, horizontal, depending on what's set. In this case, the axis direction is vertical and points down. That means content moves upward as far as the user scrolls, the default behavior in most apps. Relative to the axis, we also define two important edges, the leading edge and the trailing edge. This represents the start and end boundaries of the scrollable area, depending on the scroll direction. In addition to the main axis, there is also a perpendicular one, the cross-axis direction. This defines how layout is handled across the scroll direction. For example, horizontal positioning in a vertical scroll, or vertical positioning in a horizontal one. These two parameters, axis direction and cross-axis direction, work together to fully define the orientation of the scrollable content inside the viewport. If we have two axes in two-dimensional space, it makes sense that they intersect somewhere. And in our case, they intersect at a very specific point, known as the anchor. So where is the anchor located? It's easy to make assumption based on experience with the default viewport setting. You might think it's always the top left corner, and that's it. But that's not entirely true. Its position along the cross-axis depends on the cross-axis direction, while its position along the main axis can be explicitly configured. We can think of the main axis of the viewport as a segment, ranging from 0 to 1. By default, it is 0, 0, which gives us top left corner for the very common case when the axis direction is down and the cross direction is right. But setting the value can set the anchor to a specific point, for example, 0.5, as you can see in the example. Why do we need it? Because the anchor is much more than just a crossing point. Relative to this point, the viewport builds the content. This is another place where assumption can be misleading. By default, this central sliver is simply the first sliver in the list, unless explicitly overridden. But you can configure which sliver is considered the center sliver for this viewport. Relative to the center sliver, other slivers grow. All slivers after the center one grow in the forward direction, and those before the center one grow in the reverse direction. Apart from the visible area of the viewport, there is also two invisible zones, known as cache areas, one after the trailing edge and one before the leading edge. Why do we need them? To ensure smooth scrolling. When content enters a cache area before reaching the visible area, it gets built and laid out in advance. That way, when it actually appears on the screen, it's already ready to go. Similarly, when content leaves the visible area, it's not immediately destroyed. That's because the user might reverse direction, and we want the content to be readily available for smooth re-entry into view from the other side. The default size of each of these areas is 250, but again it can be adjusted. Based on this, the actual viewport size is visible size plus 2 cache sizes. All of these were different aspects by viewport itself, but one of the key responsibilities of the viewport is position the content in display. So the next property we're going to talk about is something that directly related to this topic. Growth direction. In a visualization, I show a common situation when the main axis is vertical and axis direction is down. All elements have a number from 0 to 7, like the order if you provide them one after another. The growth direction value can be forward or reverse, and as you can see, depending on this value, content is shown in a completely opposite ways. If every next element with the bigger number appears in the same direction as axis direction, the growth direction is forward, otherwise reverse. Another responsibility of Viewport is adapting layout in response to user action. Scrollable on its own doesn't move anything. It detects gestures and notifies the viewport that there is a user action. So what happened when the user interaction occurred and the viewport is notified? The reaction is described by parameter user scroll direction. This parameter is influenced by both the direction of the main axis and the growth direction. To make this clear, I'll show you two examples side by side, both with the vertical main axis pointing down, but with two different growth direction values. If the user isn't interacting with the screen at all, then the user scroll direction is set to idle. And even if the user touched the screen but doesn't move their finger, for example just holding still, the direction remains idle as well. Now let's say that users start dragging their finger upward. At this point, the user scroll direction values diverge between our two cases. In one configuration it becomes forward, in the other it becomes reverse, all depending on the growth direction. And when the user changes the direction of the drag, the value flip. Forward becomes reverse and reverse becomes forward. The definition can be described with a simple rule. If the movement should make the next element appear, this is forward scroll direction. If the previous one appears, this is reverse scroll direction. And now we finally arrived at the point to talk about actually content is being shown inside the viewport. The units you'll be working with if you want to implement any custom scroll behaviors, slivers. However, it's important to remember that slivers are, at their core, just render objects operating under a specific protocol. And if you want to implement any custom scrolling effects, the main area you'll be working with is layout, analyzing constraints, and providing sizes. To help you explore how this actually works, I also created a small demo app. You can use it to experiment with different scrolling scenarios and observe what constraints parameters are passed to a sliver in each case. You will find the link in the description, and you can also scan the QR code shown on the screen to access it directly. So, Sliver Constraints, what we can actually find there? Well, we actually mentioned quite a few of them, because Sliver Constraints, they not only describe layout boundaries, but also state of the viewport. Inside Sliver Constraints, you will find axis direction, cross-axis direction, user scroll direction, and many other things related to viewports, which we already discussed. In addition to those viewport state descriptors, Sliver Constraints also include the size of the viewport main axis size, the number of pixels the viewport can display on the main axis, cross-axis extent, the number of pixels in the cross-axis. Alongside this shared viewport-related information, which is the same for all sliver inside the given viewport, Sliver Constraints also provides information which is unique and specific for each sliver. Depending on the sliver position, scroll progress, what's happening with the neighboring sliver, values like scroll offset, remaining pane extent, overlap, etc. can be different. Let's check them one by one. Scroll offset describes the offset of the earliest visible part of the sliver relative visible part of the viewport. Before crossing the leading edge of the viewport, the value is 0. The default example can be a little confusing because the viewport edge is in the same place in the anchor. It's important to note that the point of calculation is the edge of viewport, not the anchor. If we move the anchor to the middle, crossing it will not make the value different from 0. As soon as the sliver crosses the edge, the scroll offset starts growing. And of course, if the axis direction changes, the leading edge also changes, so the scroll offset calculates relative to another edge. Preceding scroll extent. The scroll distance that has been consumed by all render slivers that came before this render sliver. Let's have a look at preceding scroll extent in the application. To make it easily, we'll remove up bar and add bunch of slivers before our target sliver. So we can see here with the growing this amount, we see growing this number. Then bigger amount of widgets before our sliver, then bigger amount of space we need to scroll before we reach our sliver. It looks pretty simple, but it has a tricky edge case. Often, slivers create their content lazily. In this case, when the whole internal content of this sliver is much more than the viewport size, additional content will be created only if needed, when the layout occurs. This means that the sliver doesn't have enough information to estimate its total extent, so preceding scroll extent will be infinite for all slivers after this sliver. But it will be so before all the content of this lazy sliver will be created. Then preceding scroll extent will be stop being infinite. Remaining paint extent is the number of pixels of content that the sliver should consider providing. Providing more pixels than this is inefficient. It's worth noting that this is not an obligation to provide the exact amount of pixels. It's more like a hint. This sliver is being told, this is roughly how many pixels I expect you to provide. If you need less, great. But if you provide more, it will be wasted work because of those extra pixels won't be painted anyway. While the sliver is in the visible part of the viewport, this parameter is a distance from the leading edge of the viewport to the trailing edge of the viewport. And when the leading edge of this sliver leaves the visible part of the viewport, this property will be equal to viewport main axis extent, all visible size of the viewport along the main axis. When a sliver is before the visible part, this value is also 0. This value can be infinite when the viewport is unconstrained. For example, render shrink wrapping viewport. Remaining cache extent. This one is identical to the previous one, except the borders of the measuring are not visible part edges, but the cache area. And it can be useful not for painting, but mainly for laying out. cacheOrigin, where the cache area starts relative to the scroll offset. This parameter can be quite tricky to understand if you rely only on its documentation. Several other parameters are mentioned in the cross-reference manner, which doesn't help much. But let's try to break it down and see what it actually represents. We remember that the viewport has two cache areas. One that it enters before appearing in the visible viewport area, and one that it moves into after leaving it. And layout needs to happen in those cache areas as well. Before a sliver leaves the post-visible viewport cache area, things are fairly straightforward. We need to perform a layout based on the fact that the maximum available space for it is the distance from the leading edge of the sliver to the end of the cache it initially enters. The remaining cache extent we discussed before. But as soon as the sliver moves beyond the boundary of the cache area, we need to reconsider where the layout should even begin. There is no point in laying out portions that are no longer relevant, not even within any cache area. And this is where the relation of the scroll offset becomes essential for calculating what still needs to be built. And here it's worth remembering that while scroll offset does a good job of describing how far we scrolled, at its core it actually represents the offset of the first visible part of the sliver in the viewport. That's why cacheOrigin quite literally defines how much space before that visible part still needs to be laid out. And if we return back to the definition, where the scroll areas start related to the scroll offset. The cache area that was mentioned there is not one of cache area of the viewport, but the space described by remaining cache extent. It is always negative or zero and will never exceed the cache extent absolute value. Let's explore it with schemas. Let's start with a simple case when a sliver is in a visible part of the viewport. So the first visible part of this sliver is actually leading edge of this sliver, and remaining cache extent starts exactly in the same place. Because of this, cacheOrigin is also zero. Now we can see a case when the sliver is moving out from the visible part of the viewport. The first visible part of the sliver is marked by this red line, and the scroll offset shows how far this first visible part of the sliver, and since remaining cache extent starts from the leading edge of this sliver, cacheOrigin is minus scroll offset. When the sliver reaches the end of the cache area, we face with the first edge case. In this case, there is no visible part of the sliver in the visible part of viewport, so we can consider that first visible part is the edge of the viewport, and scroll offset is equal to cache extent. And the remaining cache extent starts exactly at the leading edge of this sliver and in the end of this cache area. In this case, we can see that cacheOrigin has grown into his absolute maximum, equal to cache extent but with a minus sign. If the sliver continues moving out, and part of the sliver will be out even cache area, cacheOrigin will not grow anymore. And there is again no visible part of this sliver inside the viewport, so we can consider that the first visible part of it is the edge of viewport. And the remaining cache extents start in this case cache extend space far. So cacheOrigin will continue be minus cache extent. And even this sliver completely leaves cache area, nothing will be changed. And this schema shows exactly why this parameter is necessary. That's case we initially discussed. We have a long sliver which is partially out of the even cache area, but part of the sliver is still even visible. We need to decide from which part we need to lay out, from which part we need to render, and so on. So this is why we need this parameter. Overlap. Size between the first painted pixel of the sliver and the first not covered by previous sliver pixel. It uses for pinned or floating effects. Let's explore it with the visualization possible cases of overlapping. For example, we have a bar which is blue rectangle on this schema, and a green one is another sliver which can be overlapped by this bar. Before we start scrolling and they are just connected edge to edge, overlap is 0. If we scroll enough far to hide this up bar completely, overlap is also 0. But then if we scroll down and the up bar appears and covers part of the green sliver, there is an overlap. And this is exactly overlap in this case. If we continue scroll, a bar continues grows and partially covers this green sliver, overlap will be continue exist. And if our physics behavior allows us to move one sliver from another, like Cupertino scroll physics for example, overlap can be negative. We have talked about sliver constraints, but based on these constraints we need to provide a size after layouting. And the size in this case is sliver geometry. Let's have a look at properties of sliver geometry. First property is visible, and this one is pretty simple. If we set it false, Flutter will not paint the sliver at all. The next one, scroll extent, the estimated total scrollable extent that this sliver has content for. A simple way to say it, this is the amount of scrolling that user needs to do to get from the beginning of the sliver to the end of the sliver. This property is used to calculate an offset for all next slivers. For this reason, we should set this property every time, even if this sliver is out of sight. Commonly, scroll extent is permanent for the sliver all the time, opposite to paint extent and layout extent, which change from 0 to scroll extent, while the sliver changed the position. Layout extent, the distance from the first visible part of the sliver to the first visible part of the next sliver, assuming the next sliver constraints, scroll offset is 0. In other words, it shows how much space the sliver occupies within the visible part of the viewport. And why do we need to occupy space? Well, usually to display something there, right? That's why layout extent often matches paint extent. This is not a strict requirement. Technically, layout extent defines the bounds from 0 up to paint extent. By tweaking their relationship, you can create interesting visual effects. Paint extent, the amount of currently visible visual space that was taken by the sliver to render. It takes all sliver constraints remaining paint extent or its part. It means that the value of paint extent must be between 0 and remaining paint extent. In contrast to layout extent, this value does not affect how the next sliver is positioned. Do you remember those interesting visual effects I mentioned? Let's look at the simple one. For example, if the paint extent is 100 pixels bigger than the layout extent, for a common sliver after it means that it will be painted over in this 100 pixels. Based on this fact, it is easy to see that paint extents affect the calculation of the sliver constraints overlap for this next sliver. Cache extent. How many pixels the sliver has consumed in the sliver constraints remaining cache extent. This value should be equal or larger than the layout extent because the sliver always consumes at least the layout extent, which is in the visible part, and maybe something in the cache area. Max paint extent. The estimated total paint extent that this sliver would be able to provide if sliver constraints remaining paint extent was infinite. This is used by Viewport that implemented shrink wrapping. By definition, this cannot be less than paint extent. Paint origin. The visual location of the first visible part of the sliver relative to its layout position. By default, sliver starts painting exactly where they're layouting, so the value is 0. By changing it, we can also create interesting visual effects. For example, if we set this negative, the sliver starts to paint earlier and gets rendered underneath the previous one. If we set this positive, the sliver starts to paint after and appears above the next one. It does not affect the position of other slivers, but affect the sliver constraint overlap for the next. Heat test extent. The distance from where the sliver started painting to the bottom of where it should accept the user interaction. This must be valued between 0 and paint extent. Commonly, it is paint extent, because logically speaking, all visible parts are usually interactive. Max scroll abstraction extent, the maximum space by which the sliver can reduce the area in which content can scroll if the sliver were pinned at the edge. For example, sliver bar with pinned true. A sliver that never get pinned at the edge should return 0. Scroll offset correction describes a correction of the scroll that the parent should make. If this is non-zero after perform layout finish, the scroll offset should be adjusted by the parent. If the parent is also a render sliver, it cannot adjust it, so it should be propagate the value in its own geometry until the viewport. The viewport adjusts the offset based on this value. But how it can be used? Cupertino refresh indicator is a good example. It takes some sizes, but while it's disappearing, the size is changing. And this change, of course, affects the following slivers. Scroll offset correction is used to fix it. And the last property has visual overflow. It describes whether the sliver has a visual overflow. By default, this is false, which means the viewport does not need to clip children. The viewport will apply a clip to its children if any slivers have a visual overflow. So, we have now covered all the theoretical aspects of Sliver protocol. In the next video, I will show you how to put this knowledge into the practice and create an interesting scrolling effect. Subscribe to the channel to not miss next video, hit the like button and all that good stuff, That's all for today. It was Mikhail. Catch you in the next video. Bye!